Hello everyone, welcome to the demo of our course project. We are Team 13 and here is the name list of our group member. In our project, we aim to find the impact of air quality and weather on people's mental and physical health. In the first scenario, we plot the air quality data of Victoria, Queensland and New South Wales in 2022 on a 3D map. The data is loaded from the NAQD, the National Air Quality Database. Now let's check the air quality visualization. Once the plot is generated, user can play around with this map by dragging it to spin it and zoom in or out. User can drag on the slider or press play or pause to play or stop the auto animation. User can also put cursor on the data points to see the detailed values. In the second scenario, we perform an interaction analysis between the sentiments and the air quality. The sentiment data is extracted from the Twitter dataset from Spartan, the same as assignment 1. And the air quality data also comes from NAQD. Unfortunately, the air quality of Victoria in 2021 is not available for download, while we only have the sentiment data of 2021. To match the data's time period, we have to limit the district to Gold Coast and Sydney, where the data of most air quality sensors are available, as plotted in the previous scenario. First, we plot the overall sentiment distribution of the limited district on the bar chart. We can easily tell that this follows a normal distribution. Second, we plot the scatters of the sentiment versus PM2.5 value. Each piece of sentiment data is mapped to the average air quality value of all the sensors within the radius of 5 kilometers around it. If there is an obvious relationship, we should be able to see it on the plot. And unfortunately, there is none as far as we can see. So we need to apply some mathematical analysis. Here we use a generalized linear model, a GLM, to check the relationship between them. As we saw before, the sentiment roughly follows a normal distribution, so we chose the Gaussian family in the function. From the result, the p-value is 0.08, which is larger than 0.05. So we believe that the average PM2.5 value is not a statistically significant factor of people's mood. Now, after the mental health, let's see some physical impacts. In the third scenario, we visualize the number of asthma patients in each district in Victoria and perform another GLM with the air quality. The asthma data is from pseudo and is processed in GeoJSON form. First, we pre-process the data by merging them to the same data frame. Then we plot them on the 2D map generated from GeoJSON data. User can choose different types of asthma from the drop-down menu and see its rough distribution. User can also zoom in or out, or click or put your cursor on the districts to see the detailed values. For the district splitting, we chose the SA4 level data since the air quality sensors are not evenly distributed. If we split the district into smaller regions, the available district would be much less and may not be sufficient to our further analysis. After this, we use a scatter plot for similar purpose as we did in the previous scenario. and print the correlation. By doing this, we can see some abstract relations. Also, you can click on the legend to show or let the scatter disappear. Then we apply the GLM model. By observing the p-values, we believe that the features, the mean PM2.5 and its interaction term with the max PM2.5 are highly significant, while the max PM2.5 alone is not statistically significant. To further derive the best model, we apply stepwise selection of the features. Then we can derive the generalized linear model to predict the number of asthma patients with these values. And here are the parameters of this function. In the final scenario, we use the live data from BOM of some weather features at Melbourne Airport. First, we plot a bar chart of these features of the past few days. We can see a sort of clearly similar trend on each day. Thus, we can make the guess that some of the features are correlated with each other and the time of the day, since the curves are repeating. Here, we would like to model the impact of the other features on the apparent temperature. Similarly, we perform a GLM for feature selection. And from the output, we can tell from the result that the true temperature, the wind speed, and humidity are significant features for the apparent temperature with p-values very close to 0. Also, the hour of the day is an important factor, also with a p-value close to 0. Due to the assumption that the data follows a pattern of sequential repetition, we chose to use a LSTM model for prediction. Since it makes some time to train the model, we have pre-trained the model with some previous data and only load the model in the demo here. Also, we implemented a fission function which runs every 30 minutes to repeatedly get the live data from BOM and send to the front end. Since we don't have that long time during the demo to wait for half an hour, we wrote another function to speed up the process so that we can show how it works by pretending some download data is the live incoming data. So as we can see, the red dot at the end is our predicted apparent temperature for the next half of hour. The red line before it records the previously predicted values to compare with the true value, so that we can evaluate the model's performance better and easier. If we run this cell again, we can see that the graph keeps updating every time it receives a new data incoming from the backend with the fission function. And we can tell that our prediction model works quite well so far. And that's all for our demo. Thank you for watching.